Welcome to the deep dive. Today, we're jumping right into something pretty cool in AI diffusion language models, or DLMs.
Yeah, these DLMs, they're really powerful for generating text, right? They can create tokens in parallel, mix up the order. Theoretically, a big step up from standard autoregressive models.
Exactly, that's the theory.
Oh.
But here's the catch. In practice, they often end up being slower. All those refinement steps, the heavy computation needed for bidirectional attention, it kind of bogs them down.
It's like having this amazing engine that gets stuck in traffic.
Precisely. But what if? What if these models actually figure out the answer, like internally, way before they finish all those steps? What if a lot of that work is just extra? That's the core idea in this new paper we're looking at. Diffusion language models know the answer before decoding. They call it early answer convergence.
Early answer convergence,
Yeah.
Okay.
Yeah, so basically they found DLMs often nail the right answer internally much sooner than the final step, sometimes only halfway through the process. We're talking like 97, even 99% correct on tough benchmarks like GSMAK and MMLU, way early.
Wow. Okay, so they kind of know it, but keep going.
Seems like it. And the researchers didn't just point out the problem, they built a solution. Profit.
Profit, right?
It's this elegant algorithm, no extra training needed, works with different models, and it basically watches how confident the model is.
So it's monitoring the model's internal state.
Exactly. And when the confidence is high enough, Profit says, okay, stop refining, commit to the answer now.
An early commit.
Yep. And get this. It cuts decoding steps by up to 3.4 times without really hurting the quality of the output. It reframes the whole thing as an optimal stopping problem.
Okay, that's interesting. So it's not just about brute forcing speed, but being smarter about when to stop.
Right. It's like the model knows when it knows. Instead of just running through the motions.
That does raise a question, though, doesn't it? If they know the answer so early, is all that extra computation just noise? Or is it doing something subtle we don't quite grasp yet?
That's the fascinating part. It challenges how we think these models work.
Yeah.
It's not just reaching step Tmax. It's about recognizing that internal certainty. Can we trust it?
A very good question.
Okay, so let's back up a tiny bit.
Yeah.
Remind us, how do these diffusion language models actually work?
Sure. So fundamentally, they work by iteration. You start with, say, a sequence of masked tokens, total noise, essentially. And step by step, the model refines it, denoising and sometimes remasking parts until a coherent output emerges.
Like sharpening a blurry image, word by word.
Exactly. And their big advantage, theoretically, is that parallel generation. Unlike autoregressive models that go strictly left to right, one token at a time.
DLMs can work on multiple parts of the sequence at once, which should be faster.
Should be. But as you said, practice is different. They often miss out on things like KV cache.
Ah, right. The key value cache that helps AR models reuse past computations efficiently. Big speed boost there.
Huge. And DLMs generally don't have that in the same way. Plus, if you try to decode too many tokens in parallel too aggressively with a DLM, the quality can actually take a hit.
So you've got this tension.
Yeah.
Speed versus quality.
Exactly. Which makes this early answer convergence finding even more significant.
Right, the idea that the answer's often there, hidden inside way earlier. So the researchers, they really dug into this with LDAD, right? An 8 billion parameter model.
They did. They used standard benchmarks, GSM-8K for math problems, MMLU for general knowledge stuff, and they meticulously watched how the model's top guess for each token changed over the decoding steps.
What did that look like? Was it gradual or sudden?
Well, it really depended on the setup. Initially, using what's called low-confidence remasking and no special prompts, the convergence was pretty slow.
How slow?
Like, only about 24% of the samples had the correct answer locked in by the halfway point, and even fewer, maybe 8% by the quarter mark.
Okay, so not very early in that case.
Not at all. But then, they changed one thing. The remasking strategy. They switched to random remasking.
Instead of focusing on low confidence token, just picking tokens randomly to refine.
Precisely. And the difference was, well, dramatic.
How dramatic?
Suddenly, almost 90%, 88.5% to be exact, were correct by just 25% of the steps.
Wow. From 8% to nearly 90% just by changing how it remasks.
Yep. And it climbed to 97.2% correct by the halfway point. It shows just how much that refinement strategy itself shapes the convergence. It's not just the model's internal state, it's how we guide it.
That's a huge lever to pull. And they also looked at prompts, didn't they, adding a suffix?
They did. Something super simple, just adding answer at the end of the prompt.
Okay, like telling the model focus here.
Kind of. And even that had a big impact. With the original low-confidence remasking, adding that answer, Suffix boosted correctness at the 25% mark from that dismal 8% up to nearly 60%.
60%, just from adding one word.
Yeah. And even with the already good random remasking, it pushed the 25% number from 88.5% up to almost 95%. It helps the model zero in faster.
Incredible. But you mentioned MMLU is even more extreme.
Oh, yeah. The appendix data for MMLU is kind of mind-blowing. With the suffix prompt and low-confidence remasking, get this, 99.7% of samples got the right answer by the 25% mark.
99.7% by a quarter of the way through.
And 99.9% by the halfway mark. It really makes you scratch your head about what's happening in the other 75% of the steps.
Seriously. Is it just refining the punctuation? What's going on?
Well, their visualizations, these heat maps they show, give some clues. They plot the probability of the chosen token over time for each position.
Okay.
And you see that tokens related to the reasoning, the sort of chain of thought part, they tend to fluctuate more. Their probabilities might go up and down.
Makes sense. The model's kind of working through the logic.
Right. But the tokens that make up the actual answer, they tend to stabilize much, much earlier. They hit a high probability and just stay there, locked in.
So the core answer solidifies quickly, while the reasoning might still be shifting around it.
Exactly. They show an example where, without the suffix prompt, the answer tokens maxed out their probability around step 119 out of, say, 150 or 200 total steps they might run for. But with the suffix prompt, they max out way earlier, around step 88.
So the prompt helps lock in the answer faster, visually confirming what the percentages suggested.
Precisely. Those green boxes in their figures highlight this stable answer region. It's like the model shouts, I got this part, much earlier for the answer itself. It's ready for that early commit we talked about.
Okay, so the problem is clear. DLMs often find the answer early but keep crunching numbers. And the solution is Prophet. How does Prophet actually know when to stop?
It relies on a really neat metric they call the confidence gap.
Confidence gap.
Okay. For any given token position at a specific time step, you look at the model's output probabilities, or logits. The confidence gap is simply the difference between the score of the highest ranked token and the score of the second highest ranked token.
So the gap between the winner and the runner-up.
Exactly. If that gap is really big, it means the model is very, very sure about its top choice. There isn't a close competitor. High confidence.
And if the gap is small?
Then the model is less certain. Maybe the top two tokens are almost equally likely, lower confidence.
Got it. So Prophet is tracking this gap.
It tracks the average gap across the answer tokens specifically. Instead of just running for a fixed number of steps, Prophet constantly asks, okay, model, how sure are you about this answer right now? Using this gap measurement.
Which turns it into that optimal stopping problem you mentioned.
Right. You're weighing the cost of doing more steps, more computation, more time against the risk of stopping too early and maybe getting the answer wrong because you didn't refine enough.
How does it balance that? Is it just one fixed threshold for the gap?
No, and that's the clever part. It uses an adaptive strategy. They call it time-varying risk aversion.
Okay. Sounds fancy. What does it mean?
It means Prophet changes how cautious it is depending on how far along the decoding process is. Early on, things are usually pretty noisy. The model's predictions are still changing a lot.
Right. Lots of potential for improvement.
Exactly. So stopping too early, then, is risky. Prophet is very risk-averse in the early stages. It demands a really high confidence gap before it's willing to commit. Like, show me you're extremely sure.
It needs a lot of conviction early on.
Precisely. But as the decoding progresses, things tend to stabilize. The potential gains from one more step get smaller, while the cost of that step remains.
So the trade-off shifts.
It does. Prophet becomes more risk-tolerant later on. The confidence gap threshold it requires gets lower. It's like saying, okay, things look pretty stable. The cost of continuing probably outweighs the tiny chance of improvement. Let's commit.
That makes a lot of sense. It adapts to the dynamics of the process.
It's implemented with a neat stage threshold function. They divide the remaining proportion of steps into 3 stages. Early stage, less than a third done. High threshold, say 8.0 for the gap. Mid-stage, medium threshold, maybe 5.0. Late stage, more than 2/3 done. Lower threshold, like 3.0.
So it gets progressively easier to trigger the early stop as time goes on, assuming the confidence is there.
Exactly. It's dynamic. Once the average confidence gap across the answer tokens meets the threshold for the current stage, boom, Prophet signals to stop iterating.
And then what? Does it just output the current state?
It stops the refinement loop and then performs one final parallel decoding step to fill in any remaining masked tokens based on the current state. So you get the complete sequence out.
And you said it's training-free and model-agnostic.
Totally. It just wraps around the existing inference code. At each step, it calculates that average gap, which is computationally very cheap, compares it to the age-appropriate threshold, and decides whether to continue or stop. No model retraining needed. Works on top of different DLMs.
That's incredibly practical. Just slot it in.
Pretty much. Negligible overhead for potentially huge speedups.
Okay, let's talk about those speedups, the results section. How did Profit actually stack up?
They ran a pretty thorough set of experiments. Used LED 8B and another model, Dream 7B, compared Profit against the standard full decoding, using all 50 steps in their setup, and a simple half baseline, just stopping arbitrarily at 25 steps.
A naive approach.
Right. And they tested on a whole range of tasks: MMLU, ARCC, HelloSwag for general reasoning, GSM8K, GPQA for math and science, even planning stuff like Sudoku and Countdown.
Covering the bases. So what did Table 1 show? Did Profit live up to the hype?
It really seemed to. Consistently, Profit either matched or sometimes even slightly exceeded the performance of the full 50-step baseline, but with way fewer steps.
Give me an example. MMLU.
Yeah, MMLU on LED 8B. The full decoding got 54.1% accuracy. Profit got 54.0%, basically identical. But Profit did it with a 2.34x speed up in terms of steps.
2.34 times faster for the same score. That's significant.
Definitely. And then there was HelloSwag, which was even more surprising.
What happened there?
Profit actually beat the full baseline. It got 70.9% accuracy, while the full 50-step run only got 68.7%.
It did better by stopping early. How does that work?
The thinking is that sometimes those extra refinement steps later on can actually introduce noise or derail the model, causing it to corrupt an answer it had already figured out correctly earlier. Profit avoids that by committing when confidence is high.
That's fascinating. So stopping early can sometimes be safer for quality.
It seems counterintuitive, but the data suggests it can happen.
And what about the other model, Dream 7B?
Similar story. On MMLU, Profit had a very small accuracy drop, like 1.5% compared to the full baseline, but achieved a 2.47x speedup. Again, a really attractive trade-off.
So it generalizes across different models.
It appears so, and its strength really showed on the harder tasks too. Take GPQA, a tough science benchmark.
What?
The naive half baseline, just cutting steps arbitrarily, really hurt performance there. Accuracy dropped quite a bit, from 25.2% down to 21.2%.
Noticeable hit.
Yeah. But Profit, it managed to get 25.7%, basically recovering the full model's performance while still being much faster. It shows it's not just speeding things up randomly, it's doing it safely. It avoids the pitfalls of just guessing when to stop.
That safe acceleration aspect is key for trusting it in deployment.
Absolutely. And just for the raw speed numbers, on the Sudoku task with Dream 7B, Profit achieved its maximum reported speed up, a 3.4ax reduction in decoding steps.
Over 3 times faster.
Yeah, for tasks where the answer structure might emerge very clearly and confidently early on, Profit can really fly.
This really could make DLMs much more practical for real-time applications, couldn't it?
That's the goal. It tackles that inference speed bottleneck head-on, making these powerful parallel models more competitive with AR models in actual deployment scenarios without demanding a quality sacrifice.
Okay, so let's bring it all together. We started with this challenge. DLMs are powerful, but often slow in practice.
Right. The parallel potential wasn't fully realized because of the lengthy refinement.
Then came this key insight. Early answer convergence. The models often know the answer internally much earlier than we thought.
A fundamental observation about their internal dynamics.
And Profit is the smart solution built on that insight. It uses that confidence gap metric.
And the adaptive risk-averse stopping strategy.
To decide when to commit early, turning decoding into an optimal stopping problem.
And critically, it's training-free, model-agnostic, easy to integrate, very practical.
Making DLMs faster without sacrificing quality, sometimes even improving it slightly by avoiding overthinking.
Exactly. It complements other speed-up techniques, too. It's not an either-or thing.
It really feels like a shift in perspective. Instead of just trying to make every single step faster, it's about recognizing when the job is actually done.
It is, and it makes you wonder, doesn't it? This whole deep dive into Profit. It shows this hidden convergence happening in DLMs. What other complex AI systems might have similar hidden points of certainty, these moments where they've essentially solved the core problem but are still going through the motions?
That's a great question to ponder. Are there other Profit-like opportunities waiting to be discovered in different types of models?
Could be. It encourages looking beyond just the final output and understanding the internal journey better.
Definitely food for thought. And for anyone listening who wants to dive even deeper into Profit itself, the code is open source.
That's right. You can find it on GitHub. The repository is linked in the paper. It's under github.com/pixeling99/profit.
Excellent. So you can check out the implementation details yourself. Well, that about wraps up our deep dive for today. Really fascinating stuff.
Agreed. A clever solution to a practical problem.
Thanks for joining us, everyone, and we'll catch you on the next deep dive.